Hi, I'm Kirk Weiler, and today we're going to be talking about compound interest in Math 4 honors. So, this is a topic that's very, very appropriate in this unit because it's one of the most common real-world applications of exponential functions. When we get or invest money, let's say, or even have debt, but let's talk mostly on the positive side. Let's say that we're investing money in something that guarantees a given return. These things would be like United States Treasury bonds, CDs, even some investment vehicles will guarantee you a % return. But when we do this, we're getting to apply a constant % per year often. So something will say we guarantee that you're going to get 3.5% per year in terms of interest. And of course what that would mean was that you'd get to multiply the balance by 1.035 at the end of each year. So, we're going to be looking at a lot of terminology that's used in the financial industry today. And although it may seem a little bit arcane in terms of the language, try to understand it. Keep in mind that sort of the investments banking portion of our economy is absolutely huge. So it's something that you definitely want to know something about. Let's take a look, though, at exercise number 1 to get us going. All right. In exercise number 1, we're asked, what is better, earning 1% interest on savings per month or earning 12% interest on savings per year? And then I say use a principal balance of $1,000 if you need to, although, honestly, it doesn't make a difference. Pause the video right now and play around with this and see what you can come to. All right. To really understand which one of these is sort of better, what we really have to do is compare apples to apples. And you'll hear me say that a lot, meaning that what we always want to be doing is comparing things on the same time frame. See, it's very hard to compare what you're getting in interest per month to what you're getting in interest per year because they're different time periods. And some people, of course, might be fooled into thinking, well, they're exactly the same. If I get 1% per month, then I'm going to get 12% per year. But that's not true. Let's say we actually just explored this in a very logical way, which was calculating how much we would have at the end of 1 year if we did the monthly compounding, and compounding is how often you apply the interest, versus yearly compounding. All right, so what we're told is that we're going to get 1% per month, so obviously we get to apply that 12 times. Now, what I think is very interesting and important to look at is actually just what that number is. So you could do this calculation all at once on your calculator, but it would sort of miss the point. That number ends up being 1.1268, etc., which gives us a total of $1,126 and eventually 83 cents. That was an ugly 3, even uglier dollar sign, right? Versus the yearly, right, where we've just got 1,000 times 1.12 to the first. As weird as this is going to be, I'm going to write this actually one more time, right over here, because this is actually the step. Let me change the color on this. I really want to emphasize this. This is the step where we really get to compare apples to apples, right? And the reason is because we have the same time frame. We have 1 year at this point. Right? And what we're seeing, which is very clear, I hope, is that when we compound monthly, we're actually effectively getting 12.68% per year, versus when we compound yearly, we're just getting, well, even though it seems a little silly to add these 2 zeros on, so that we have sort of the same accuracy. Right? So we're getting a better interest rate there. All right. So this gets us into some interest rate terminology, and this can be very, very confusing for students, all right? Because the real sort of technical terminology is very strange, right? And so let's just take a look at it a little bit before we jump into the math, right? So we've got 2 types of rates in financial circles that you hear talk about a lot. You've got what's called your annual percentage rate, also known as your APR, or abbreviated as APR, and this is known as the nominal rate. Now, I really like this piece of terminology. I would highly recommend, and what I always tell my students is, this is what I really want them to memorize: nominal rate versus effective rate. These pieces of terminology, the annual percentage rate and the annual percentage yield, they sound so similar. But the nominal rate, right, that is the rate that banks are going to tell you. They're going to say, you're getting a 5% return on here. Nominal. But the word nominal from English, or this word nominal, not the word rate, means in name only. In other words, if I say that you're getting a nominal rate of 5%, you're not really getting a rate of 5%. I'm just telling you are. So what rate are you really getting? Well, that's your effective rate. All right. So this is what you're really getting, and that makes sense. Effectively, right? Effectively always means what you're actually having happen. So let's kind of get into some problems and see why these things would be different at all. Exercise 2 says, going back to exercise 1, if an investment is made with a nominal yearly rate, again, let's highlight that, because that's the important terminology. A nominal yearly rate of 12%, but is compounded monthly, what is the effective rate, which is also known as the annual percentage yield? All right, believe it or not, we already have the answer to this. But if we didn't, this is what we'd do. All right, we'd say, okay, well, they're telling me that I'm getting 12%. Now, normally what would happen is I would just take a 1 and add to it 0.12. But because I'm compounding it monthly, what I'm going to do is I'm going to divide that by 12. Now, that's where we got that. Remember, back in our calculation, we had 1.01, right? But remember, I'm sort of telling you, hey, I've got a nominal rate of 12%. But then what happens is I actually have to raise it to the 12 because I want to get the yearly rate. When I did that, remember, I wrote that intermediate answer where I had 1.12682, etc. This then becomes what you really multiply by, right? You're not multiplying by 1.12, you're multiplying by 1.1268, what you really multiply by. All right? And that means that our effective rate is 12.68%, right? Because that's what we're really effectively getting. If you wanted to know what you would multiply by at the end of the year, just one multiplication, you would multiply by 1.1268. Now, that's not what's actually happening. You're multiplying by 1.01 12 times, right? That's exactly what this is. This is multiplying by 1.01 12 times. But you could achieve exactly the same effect as multiplying by 1.1268 once. All right? Effective versus nominal. Exercise 3. A credit card charges a nominal 8.4% yearly interest on debt charged to it, compounded quarterly. What is the effective yearly rate they are charging? Round your answer to the nearest hundredth of a percent point. So if you think you understand the idea now, pause the video and try to figure out what that effective yearly rate is that they're charging. Go for it. All right, so let's get back into it again. I want to highlight some terms here. It's really, really important. Nominal, in name only, nominal. Okay, how often are they compounding it? They're compounding it quarterly, right? 4 times a year, and I'm looking for the effective yearly rate. All right, so let's think about this. What's actually going on? Well, we want to really just think about that multiplier. Now, what we've been told is that we're getting 8.4%, but we're compounding it quarterly. So I don't get the 0.084 each quarter, right? That is my nominal yearly. That's what the bank tells me. So I'm going to have 1 plus my quarterly divided by 4 because that's all I'm going to get each quarter. Okay? So this is literally, if you want, my quarterly multiplier. But then what I'm going to do is I'm going to raise it to the fourth to turn it into a yearly. Boy, I'm having a problem here today. Multiplier. All right, anyway, when we actually do the calculation, excuse me for my very poor handwriting, we have 1.086683, etc. Anyway, so what that's going to tell us is that we're actually getting 8.67%, right? We went to the nearest hundredth of a percentage point. 8.67%, right? It's right about here. So, have you noticed something? So far, in the last example and this example, the effective rate has been greater than the nominal rate. And that is generally always going to be the case. Generally always going to be the case, with really the one exception being if you compound it only once per time period. Typically the time period that you're always benchmarking to is the year, right? That's the way we always think about things. How was 2013 compared to 2012? Even in financial terms, that's the way we think about it. It would be very weird to think about things on a different time scale, although sometimes they do. All right, let's take a look at exercise number 4. Let's do some more comparison. In number 4, it asks us, is it better to invest in a certificate of deposit, a CD, that claims to return a nominal yearly interest of 4.5% compounded daily, or a CD that claims to return a nominal yearly interest rate of 4.6% compounded monthly? So it's this trade-off. And one thing that you learn very quickly is that the more often you compound, the higher the interest rate you'll get. So, here we're getting 4.5% but compounded daily versus 4.6% compounded monthly. The question is, which one's going to win out? Now, this is kind of a messy problem, and you got to be very, very accurate to tell the differences. So try to set up your calculation as much as you can, kind of in a large expression form, and then evaluate it all at once so that you avoid rounding errors. But pause the video right now. At this point, you probably should have the ability to compare these two. All right, let's take a look. What do we want to do? Let's lay out the daily calculation here, and let's lay out the monthly calculation here. And what we're going to do is we're going to turn both of them into yearly calculations. All right, we want to do it all at once. So what did we get? For daily, we got 0.045, right? But we're getting that every day for 365 days. We're not getting that. I'm sorry. We're getting that divided by 365, right? So this is now our daily rate. To get our yearly rate, we're going to raise it to the 365th power. It's really important to put it into your calculator like this because there'll be no rounding issues that will occur. When we work this out, we have 1.04602, etc. I'm not really sure how many of those decimal places I need because I need enough to be able to compare it effectively to monthly. But now let's do the monthly calculation. What's it going to be? It's going to be 1 plus 0.046 divided by 12. That's what I'm going to get to multiply by every month, but then I'll raise it to the 12th to turn it into a yearly multiplier. And that's 1.04698, etc. I think you can tell pretty quickly, even though that they're close, 4.602%, 4.698%, the monthly wins. You might say that it's not enough to really care about, but that all depends on how much money you've invested. So if you're going to invest $1 million in a CD, you want to get every little bit you can. You want to get every little bit you can if you invest any money, but the more you invest, the more that little discrepancy in the decimal place makes a difference. All right, let's take a look at the last topic. All right, what we're going to eventually get into is the idea of what's known as continuous compounding. And continuous compounding is fantastically interesting to think about. We can easily take a nominal yearly rate and divide it by however many subdivisions we want. Monthly, we divide by 12, quarterly by 4, daily by 365, what have you. So you can imagine that we can divide by greater and greater amounts until the point is that we're essentially compounding on a continuous basis every moment. You don't even want to think about it as every second. You want to think about it as literally time just kind of being continuous and always applying this interest. But it's kind of fascinating because one would almost think then that the interest rate would just keep growing and maybe even head towards infinity, which isn't what happens. But let's take a look at what does happen. Take a look at number 5. It says, let's say we have a nominal yearly interest rate of 5% compounded hourly, with parentheses, which is fairly often. Determine the effective rate. Write out every decimal point your calculator gives you. Now evaluate e to the 0.05. All right, so this is going to kind of bridge the gap with what we did in the last lesson with continuous growth. Now, what would really be nice is for us to be like, hey, let's compound every nanosecond. You know, that would really get us close to instantaneous, but the plain fact is the calculation would just be laborious. So let's do it every hour. All right, now we have to think kind of carefully about this because we have to think about how many hours are in a year. Right? Well, I know that there's 365 days in a year times 24 hours in a day, right? Maybe I would want to work this number out first. Depends on how confident I am with parentheses use in my calculator. That's 8,760. All right, and then I'm going to raise it to the same thing, to the 8,760. And what I'm going to get, and watch this, I want every decimal place, is 1.051270,947. On the other hand, if I do e to the 0.05 on my calculator, I get 1.05127109.6. Now I really want you to understand what that means. Right? Take a look at how close these are. Right? They are so close. And it basically means that multiplying by this quantity, which is what I'd multiply by, right? That's what I'd multiply by every year, is the same as multiplying by this quantity. And in fact, this is how we're going to do continuous compounding. That's what we're going to multiply by. So let's take a look at this. It's one of the most famous equations in all of finance. It's sometimes referred to as the PERT equation, because it basically says, look, if we're going to compound continuously, and sometimes this is just the way banks think about it, and the reason why, by the way, why it makes sense for banks to think about it this way is that if you deposit money into some kind of an account, let's say, and it's compounded yearly, what that means is you don't get the interest until the end of the year. So if you pull your money out after 11 months, you're out of luck. You don't get the interest. And that kind of stinks, right? Because as an investor, it cuts down on your flexibility. You want to be able to put money in, take it out, put it in, take it out, right? And if it's compounded even, monthly, you're still restrained by the month. Maybe you want to be like high speed trading or something like that. What instantaneous compounding does is allow you to withdraw the money after any amount of time and still earn an interest rate based on some kind of nominal percent. Did that make sense? It made sense to me. I kind of like that. Anyway, so let's look at the equation. It's very famous. It says, if we're told, let's highlight some important things. If we're told that we have a principal, so an initial amount of money, it's put into an account that earns an interest rate R, all right, and that's really a nominal rate, and it's compounded continuously, all right, then how much money we'll have in there after t years is given by the principal times e raised to the r times t. And let me point out some other things. This is a nominal rate. It's not actually what you're getting. Sometimes it's called the instantaneous rate. All right. The r is in decimal form. All right. So if you had 5%, as we will in the next problem, it'll be 0.05. So let's take a look. It's a very simple formula to use. You just have to know when to use it. That's probably the hardest thing about continuous growth at all, from the last lesson or this lesson, is you have to know when to go to the natural base e. So let's take a look. An investment company promises to return a 5% nominal rate compounded continuously. So 5% yearly interest compounded continuously. This is such an important word. Such an important word. So important, we'll highlight it 4 times. On a particular bond fund they sell. if a person invests $2,000 in this fund, let's do the following. Let's write an equation that predicts the fund's worth A, I guess A for amount, as a function of the number of years. Alright, so A equals P times E to the RT. Alright, very simple. A is our principal, so that's going to be $2,000. E is just E. R is 0.05 to the T. By the way, one thing I should have pointed out about this formula, that was absolutely brilliant, is that really where this thing all comes from, and it's somewhat lost in the formula itself, is the fact that what we're really doing is we're really multiplying by e raised to the r every year, right? That's what that last problem was really supposed to get at. But then we use the exponent law that says you can multiply two exponents together, right? But literally we could just replace this. Now letter B says determine the effective annual rate of this investment. See if you can figure out what this is. Pause the video for a second. Did you figure out that it was 5.13%? I didn't tell you what to round to. My apologies. Right? So there's a lot of different ways that you can think about this, but the way that I really want you to look at it is the following. Right? What we really have is we're really taking this number and multiplying the principal by it every year. So this gives us our effective rate. I'm not going to say it is our effective rate, but it calculates it. So when I do e to the 0.05, right, and I get from up above 1.05127, right, remember we did this calculation up above, I can now say that my effective interest rate, sorry, it's not equal to, but is 5.13%. All right, let's do one final exercise. Which is a better investment, an account that pays 8% nominal interest rate compounded quarterly, or an account that pays 7.95% interest rate compounded continuously? All right, so what I'd like you to do is pause the video now, compare apples to apples, and make sure you know what the effective rate is for both of these two investments. Pause the video. All right, let's take a look at this last comparison. Now, again, always make sure you understand the time frame. We're given nominal rates here, right? We got an 8% nominal rate compounded quarterly and a 7.95% compounded continuously. So let's do, I say quarterly first. I think I'm going to actually stack these one on top of each other. So for quarterly, I'm going to say, well, I have 1 plus 0.08 divided by 4, right? That's what I would get to multiply by each quarter. But then if I raise it to the fourth, I'll figure out what I multiply by each year. That's going to be 1.082432216. Again, how many decimal places I need is really questionable because I don't know how closely they're going to match. So let's go with the continuous. Continuous calculation next would say, oh, well, now we're multiplying by e to the 0.0795. Just make sure that decimal place really shows up, right? That's what we're multiplying by. So, if you think about it again, the formula would have been this to the t, but the real idea is that this is what we're multiplying by. So, if we just do e to the 0.0795, we find 1.0827456, and again, maybe to the nearest hundredth, that would be 8.27%. This would be 8.24%. So our continuous wins. Now, of course, even if continuous didn't win, if it was close, we might still go with the continuous compounding because we want more flexibility with our money. Again, the idea of continuous compounding, although very, very strange, is simple. It gives you more flexibility. It allows you to deposit money and withdraw money and always be able to get some interest on it. Whereas quarterly, monthly, and certainly yearly compounding, the problem with those is that you're restricted in terms of when you can pull the money out. Alright, well thank you for joining me for another Math 4 Honors lesson. I hope this helped you understand a little bit more about nominal and effective interest rates. Until next time, keep thinking and keep solving problems.